Hi everybody. In our previous video we described the unit circle and some of the properties associated with that circle. In this video we are going to describe the 6 circular functions. Spoiler alert, it turns out the 6 circular functions are the 6 trigonomic functions. As I mentioned before, we are going to describe these functions from 3 perspectives. We've done 2 of them already, basically the standard angle perspective, the right triangle perspective, and now we are going to do it from the perspective of a unit circle. As you recall from our previous video, a unit circle is a circle which is centered on the origin, has radius 1 unit, whatever unit of length you want to use. And if we have a central angle with an angle measure of theta radians, then the arc length associated with that, the arc length intersected by that standard angle, is going to have this distance theta. So with that in mind, we can actually figure out what the x-coordinate and the y-coordinate of this particular point is. Now remember, cosine of theta, defined using our standard angle perspective, which is exactly what we have here, is equal to x divided by r. But in this case, r is equal to 1. Okay, and that basically implies that x is equal to cosine of theta. Okay, using the exact same argument for sine, we have sine of theta is equal to y over r, and that would imply, since r once again is equal to 1, that y is equal to sine of theta. So since this has a radius of 1, this point has an x-coordinate of cosine theta and an x-coordinate, y-coordinate of sine theta. And since our arc length is equal to theta, we could also say that the x-coordinate is cosine of s, and the y-coordinate is sine of s, which again, where s once again is equal to theta. So we have defined the first 2 of 6 circular functions, and we can immediately go ahead and define the other two, the reciprocal functions here. If cosine of theta is equal to x, then secant of theta is equal to 1 over x. And it's defined as long as x is not equal to 0. And finally, cosecant of theta is equal to 1 over y, provided that y is not equal to 0. You can also go ahead and define tangent. Tangent of theta is equal to y divided by x. And that is defined once again wherever x is not equal to 0. And then cotangent of theta is equal to x divided by y, of course, which is defined when y is not equal to 0. Now there is one big difference between the unit circle perspective and the perspective of a right triangle or the perspective of an angle in standard position. And that is that the angle or the arc length can be any point on the real line. In other words, theta can basically spin around in this direction as long as it wants until it approaches positive infinity, or it can spin around in the negative direction for as long as it wants until it approaches negative infinity. Accordingly, the arc length, which by the way is equal to theta, can do the exact same thing. So I know I have them written down here, but in this slide, I have them summarized yet again. Here, instead of defining it in terms of theta, I defined it in terms of s. But keep in mind, arc length and theta are exactly the same thing. So I can define it in terms of an angle, and I can define it in terms of a length, which is a very useful thing. Okay, but once again, here's what we have. We have that sine of s, or theta, is equal to y. Cosine of s is equal to x. We have the reciprocals, which can only be defined when x is not equal to 0 here, and y is not equal to 0 here. Tangent, which of course is sine over cosine. That prime is a mistake. That shouldn't be there. Is y over x. And then of course cotangent of s is going to be its reciprocal. And remember, s and s or theta can basically take any value between negative infinity and infinity. Now the last thing that I want to talk about here are the domains of our circular functions. Now keep in mind the domain can be any point on the real line where the function happens to be defined. For x and y, that for sine and cosine, that's not a problem because sine is equal to y and cosine is equal to x. So their inputs can span the entire real line. Any value between negative infinity and infinity will produce for you a value for these particular functions. Now, what do they look like? Well, here is our cosine function, and as you've seen before, when theta is equal to when s or theta is equal to 0, cosine is 1. When s or theta is equal to a negative pi, cosine is negative 1, and of course pi over 2 and 3 pi over 2 is equal to 0. For sine, as you might expect, it is equal to 0 when s is equal to 0 or pi, and it has its maximum of pi over 2, 90 degrees, and its minimum at 3 pi over 2, 270 degrees. Okay, but nonetheless, what you can see here is that any value of s or theta is going to be part of the domain for sine and cosine. That all changes when we get the tangent and secant. Why? Because we have s in the denominator, or x in the denominator. As a consequence, whenever x is equal to 0, well, we have division by 0, and they are not defined at those particular points. And that occurs at any odd multiple of pi over 2. And you can actually see this from the graphs here. Notice that we have vertical asymptotes at negative pi over 2, 3 pi over 2, and so forth. And as you can see, the functions are not defined at those particular points. Now, what you will also notice if you look at the graph of tangent is an odd function. It actually has symmetry about the origin. On the other hand, secant here is an even function. It actually has symmetry about the y-axis. But we will talk more about these graphs later in this particular chapter. Okay, for cotangent and cosecant, they are undefined whenever y is equal to 0, and that occurs at multiples of pi. When y is equal to 0 right here, that we have a vertical asymptote when y is equal to pi over here. Y is equal to 0 here. Here, y is equal to 1, but it's equal to 0 here. We have another vertical asymptote, so we get an equation. So we actually have situations where for both of these functions, they are undefined at even multiple of pi. There's a vertical asymptote at every single even multiple of pi. What you'll also notice about cotangent is that cotangent is also an odd function. It's not pretty obvious to you, but there is symmetry right about this origin, and you can sort of see the symmetry here. And it also turns out that cosecant is also an odd function. Cosecant of pi over 2 is equal to negative cosecant of negative pi over 2. So we also have the same odd symmetry. We also have the same odd symmetry about the origin here as well. But once again, as I mentioned before, later in this chapter, we will talk about these graphs in a fair amount of detail. But until then, this is all that I have. So this is Bob Boyle.